All right, so what we're going to do is we're going to review some things, and we're going to work some of this out together. Some of these I'll have you do, and you just fill these out as we go. Okay, so a function. Hopefully everybody is familiar with what a function is, because that's all we're going to talk about all semester is functions, okay? So a function basically just means that you have two things. You have the first set that we call the domain. You have a set of x's, which is the domain, and then the corresponding in the second set we call the range. But what it is every element in the domain has to go to exactly one element in the range. Okay, so it's a special relationship between two things. Oh, I didn't want it to do that. Okay, yeah, I'm good. All right. Okay, so here's kind of the idea with this, okay? The domain is the set of all x values. So I do want you to write that down, okay? You need to know that the domain is all the x values when you're talking about a function. Okay, what's the range? It's all the y values, okay? The second element's like that. Now, what you get is these things that we call like a mapping diagram. So you have like a domain. You have an x and you have a y, okay? In order for something to be a function, every x has to have exactly one y. Okay, it's got one output, in other words. So what you're doing on this one is you're taking this number and raising it to the third power. So like if you took 2 to the third, you get 8. But you get one answer, right? Every input gives you one answer. That's why it's a function. Okay, so yeah, that would be a function because every x goes to one y. Okay, next one. Now this is like a square function. Okay, this would be like now 2 to the second. When you do 2 to the second, how many answers do you get? You get 1. That's what makes it a function, okay? If you got 2 answers when you did an operation, it's not a function anymore. So this is also a function. That -2 has one answer. -1 squared is 1. It has one answer and so forth, so that's a function. Does that make sense? Every x provides one answer to y. That's what a function is. Okay, how about the next one? This is a square root. So if you did like a square root of 9, you can actually get a 3 or you can get a -3. There's 2 answers. So is that a function? No. The idea is anytime that you have something in the domain and it's giving you more than one answer, then it's not a function. That's the idea. All right. Does that make sense to everybody? So some things are functions, some things are not. Okay. We're going to deal mostly with functions. So this diagram down here, generally your input is your x value. We usually call that the independent variable. And your outputs are the y's. We call that the dependent variable like that. This is a function. Notice that the 1 goes one place, the 2 goes one place, and so forth like that. All right, you guys learn this in finite or college algebra or something? Okay. All right. Now what I want you guys to do is just go to the next page and do these 4 problems. I'm just going to give you a few minutes to do these. Now, if I want you to do the domain, let's just do the first one together here. So would this be a function on that example 1? Yes or no?
Yes.
Yes. How come?
Because each x has one corresponding.
There you go. Each x has exactly one y, so that's a function. What's the domain? That's whatever x is. So what you do is you write this like this. You usually write like a set brace like this. Then you just say 4, 8, 12. You just list the elements. That's the domain. What's the range? The range is the y values. So you just list out 0, 10, 20, like that, and so forth. Okay? All right, go ahead and do the next 3 problems there. And I'll pause it and give you just a few minutes to do that and see if you're on track with it. Okay, so how about example 2? Is that a function, yes or no?
Yes.
Yes, okay. That's fine. The question is everything in x goes to one thing in y. That is definitely a function. What's the domain? It's just the people in the set x. That would be Ken, Carl, and Lewis. Okay, what's the range? It's just one person. That's Kathy. So that is a function. Every man has, I guess, one girl he's got a crush on. Okay, you can think of it that way. That is a function. How about example 3? No? Okay, what's the deal with Jerry? Kind of a bad boy, isn't he? Okay, so that's definitely not a function. Okay, that's the idea is Jerry has 3 girlfriends, so that's definitely not a function. Well, the domain would just be him And then the range would just be these people. I'll just abbreviate those like that then, okay? All right, that's the idea. How about the next one, example 4? That wasn't in a what we call a mapping diagram to the table. Is that a function or not a function? Okay, let's see, okay? -2 has one answer, right? -1 has one answer. 0 has one answer. 1 has one answer, and so does 2. Okay? The idea is, now you don't have to write this on your paper, but really if you wrote this down, this would be x, that would be your domain, and it basically just goes, the -2 goes to 2, the -1 goes to 4, the 0 goes to 2, the 1 goes to 4, the 2 goes to 2. If you have any trouble seeing that, you can write that mapping diagram out if you want to like that. So that is a function, and then the domain, it doesn't matter what order you put these in, but the preferred way is just numerical order. The range would be, now you don't have to write 2, 4, 2, 4, 2. What do you write? Just 2, 4. Okay, there's only 2 elements, so if you didn't do that, correct yourself. There's only 2 elements, okay? All right, does everybody feel like they understand what a function is? Okay, all right. Now we're going to get into this a little bit more geometrically on the next page. And in college algebra or finite, usually we talk about what functions are and what the vertical line test is. And this is just a simple test that if you have a graph, you can tell if it's a function or not. So the idea would be if any vertical line passes through exactly 1 point, then the graph represents a function. Okay, if you can find a vertical line that passes through 2 or more points, then the graph is not a function. It's the same thing. Every x has to have one y. If you find an x that has 2 or more y's, then it's not a function. Okay, so here's the idea. If you took like a vertical line on that, how many points does that go through? It goes through 2, so that's not a function. Okay, and the idea would be, let me just kind of use this as an example. Like it looks, this looks like that might be the point 2, 2, and that might be the point 2, -2. See, the idea is this x has how many y's? It has 2, so it's not a function. Okay, that's what the vertical line test does. Okay, now if you go to the next one, that vertical line goes through 1 point. In fact, every vertical line that you can possibly draw on here goes through 1 point, so what do you conclude? Yes, that's a function. Okay, it just means every x has one y. Okay, so you can't have like something like this or a circle or something like that. It's got to be something where the vertical line only goes through 1 point. Okay, here's something that you would study in like economics or business, like average cost and market price and stuff like this. Does that look like a function to you? Yeah, that's a function. Passes the vertical line test. Okay. How about the next one? That's something you'd study in engineering or like trigonometry or something like that. That's called a cardioid, okay? You learn about that in electronics and stuff. Is that a function?
No.
No, okay? It's got two y values for the same x value, so that's not a function, okay? Okay, now let's do, what I want you guys to go ahead and do is example 6. I want you to take the time to do this. Go ahead and plot these points, and then tell me if it's a function or not. And remember, it is only a function if every x has exactly one y. That's what you're looking for. Yeah, the -4 does too. I mean, you can actually tell by not even graphing on this. I wanted to do this. I want to make sure everybody knows how to plot points and everything too. So the first one, you're going left 4 and then up 5. Now, if I have you plot points, I like you to just kind of put the letter by it. The next one, -3, 0, you're going left and then stop. Don't go up or down. And the next one, this is what makes it not a function. You're going left 4 and you're going down 5 like that. That's C. Now, see, if you did a vertical line right there, that would pass through 2 points, wouldn't it? Okay, so that's not a function. I mean, you could even do the vertical line test right there if you wanted to. That's not a function. Okay, then 0, 0's in the middle. The next one is -3, 3. I may have got a little bit off there. There we go. -3, 3. That would be another place on here that would fail the vertical line test, right? Okay. And then the last one, the last 2 points you get is you got 1, 4 over 1 up 4, and then over 2 up 4 like that. All right, everybody good with plotting points and everything? I never know when I teach a class like this what background issues are, and a lot of times there's lots of background issues students have. Okay, so that's not a function. That's the idea. All right, so the idea is we're going to kind of start, calculus kind of starts with the idea of a limit. So I'm going to introduce you to that idea today. And one way to explain this idea is you can go back into the Greek civilization. There was something called Zeno's paradox, and people had no idea how to solve the problem. We know how to solve it now. We solve it with calculus. But the idea, there's two ways you can look at this. One thing is basically this. Like if you're a football fan, okay, say for instance you have the ball on the 1 yard line, and there's the goal line, okay? If the defense jumps off sides, they penalize you half the distance to the goal line. So now the ball would now be on the half-yard line. Well, let's say the defense jumped off sides again. Well, then the referee would put the ball halfway there. What if the defense just infinitely jumped off sides? Would you ever get to the goal line? No, not quite, but you would be getting closer and closer to it, wouldn't you? Okay, that's the idea. Now, what Zeno's paradox is really saying is something similar to that. The idea would be that if I'm going to travel from here to that wall, according to Zeno's paradox, I'll never get there. Because what I have to do is I have to go half the distance and keep going half of that next distance. I'll just get infinitely close to the wall, but I'll never make it. Well, we know I'm going to get to the wall, right? Okay, so there's some sort of a paradox there, and it's really at that point in time in the Greek civilization, it just seemed like it doesn't make any sense to anybody, but calculus and the idea of a limit solves the problem. So here's kind of a little thing that I found on the internet that shows you what Zeno's paradox does, okay? It's kind of like there's a race between the tortoise and the hare. Okay, the tortoise gets a head start, and what we're going to do is we're going to go to the halfway point. So after one increment, like this, we go to the next level on here, goes like this. Next stage, okay, like this. Okay, both of these things have gone halfway to the flag. Then we do it again. Okay, then we do it again. Now the bunny is getting closer to the turtle, right? But the idea is, who's going to win this race? Is the bunny ever going to get ahead of the tortoise? No, that's what Zeno's paradox is because you keep just going over and over again. See, like right now, the tortoise is 96% the way to the flag, the hare is only there, and so forth. So if we keep going all the way in, now I'm at level 15, the idea is, see that the turtle is still a little bit ahead of the turtle, and always will be, okay? So that's what Zeno's paradox is. Well, the idea is those decimals are just going to get longer and longer and longer. So if we went not to level 15, but to level 1,000,000, well, the turtle would still be ahead, but the decimals would be way, way out there, right? That's the idea. So if we go to level infinity, then what happens? Then they really are exactly at each other. That's the idea. So the idea with a limit is, the limit is kind of where we're going. Okay, we're going, if we're going to the infinite level, we're eventually going to hit that flag. That's the idea. Okay, that's the idea of what a limit basically is. Okay, all right. Now, let me go to the next page, and we're going to do just a couple of things. If you have a calculator and brought one with you, you get it out. If you don't have one, it doesn't matter for today, but it is helpful in this class to have like a TI calculator. You don't have to have one, but it'll come in handy. And I use a calculator a lot because it's a good teaching tool. Okay, so what I'm going to do with this problem is we're going to graph this thing by hand, and then we're going to do this with our calculator also. I want you to know how to do graphs on a calculator. That's important. Okay, so first of all, from your guys' background, what does the graph of 3x minus 4 look like? It's a line, right? Okay. And you may remember, what is that negative 4? Good. Y-intercept. What is that 3? Slope. Okay. Well, let's just graph this out by hand, first of all. So, yeah, what you do is you have a y-intercept of negative 4, so you want to put a dot there. If your slope is 3, you can put that over 1. And remember, the slope is a rise over a run. So it really means that you're going to go up 3, then you're going to go to the right one, right? Okay, from the point you already plotted. So we're going to go 1, 2, 3 up and over like that. Just do that a couple of times, and then that'll give what the graph of that looks like. Everybody familiar with lines from their background? Okay, that's important. There's a lot of little background issues going to show up in this class. Y equals mx plus b is a standard form for a line, where b is the y-intercept and then m is the slope. Okay, if you don't know that, you need to review that some. Now, what I'm going to do is have you put this on the calculator. There's some things that you might not know about the calculator. It just depends on what classes you've taken. So what I'm going to do is I'm going to press y equals, and I'm going to put in 3x minus 4. So I put the 3 in. Now, a lot of times I see students searching for the letter x. Don't do that. Just go there. That's your variable button right there where it says xt theta n. Just press it, and that'll come out. And then you have minus 4 like that. So we're going to graph that, okay? Now, what I'm going to do is I'm going to make this window. I want to show you how to work with a window if you don't know this. So if you press your window button, then you would want to start, let's start at -8. Okay, that's where this graph is starting. That's what I provided for you. Then x max, go up to 8. And then we can make this go up by 2 or 1 or whatever we want to. I'm going to make it go up by 2 just because that's kind of the way I scaled this, but that's up to you. Okay, I'm going to do the y's the same way. -8 is your y minimum. Okay, and then I'm going to go all the way up to a maximum of 8. And then scale by 1 or 2. Okay, what you scale by is your choice, really. So then what you do is once you have that put in, you press graph, and then you'll get the same line that's going to come out. And what this is this again is going 2, 4, 6, 8, just like our graph is. Is everybody familiar with that? Because not all students are. If you need help with your graphing calculator, you may need to come by and see me some. But we'll go over this a lot in class, okay? Now, what I'm going to do is we're going to fill out this table of values, okay? And there's a reason why we're doing this. So what we're going to do is we're going to do 1.8. Now, what we're really doing is if we plug in 1.8, we're doing 3 times 1.8 minus 4. Now, we're going to do this in a very fast way, though, because I don't know if everybody knows how to do trace or not, but you could do 3 times 1.8 like that, and then minus 4, and we're going to find that corresponding y value, and then let's just record that as 1.4, okay? Now we're going to speed this up, okay? In this class, and you know, if you're working with technology, in the modern world we use technology for all kinds of things, you don't have to do that over and over again. You can just do your trace button, and if you haven't done this, make a note of how you do this. You type trace, then you just type the next value, which in my table is 1.9, press enter, and then you record what it says. So my graphing calculator up there is saying 1.7. Then you just keep doing that over and over again. Now, most of the time, all you got to do is type trace 1 time. So I'm going to just keep doing this. 1.99 is the next one. Okay, press enter, and then I'm going to record that now as 1.97. And I'm just going to keep doing this. Next one is 1.999, and then that's going to be 1.997. Then I go to 2. That's going to give 2. And then I just keep doing this. 2.001. Now let's see, that's 2.003. 2.01 is going to give 2.03. And then 2 more I'm going to do is 2.1 is 2.3, and then I'll finish up with 2.2. Okay, and this is the kind of thing, if you're doing this on your calculator with me, if you're having trouble with your trace button, you might want to see me after class or something so I can kind of help you and see if there's something that's not set up right on your calculator. Okay, but that's the idea. Everybody okay with what I did on that then? Okay, you can trace values out on your calculator once you get it graphed. Okay, so we're going to introduce this idea of a limit. Now, the idea on this is actually pretty simple. Is when you're getting close to 2, what is this y value getting close to? Okay, that's 2.6, 2.3, 2.03. Isn't that getting close to 2? And if you go this way, if you're coming from behind that number, that's getting closer and closer to 2. What I'm wanting to show you is these things are heading towards 2. That's the idea of what a limit is and what we were doing with Zeno's paradox. So the notation that you're going to learn is we're interested in, we say the limit of the function, which is 3x minus 4. This says x approaches 2. So when x approaches 2, what's happening is you're approaching that value right there. So the value of that limit is 2. So the idea is going to be, just to kind of get us started on this, is if you go that way and if you go that way, you're getting closer to 2 and you reach 2, don't you? That's the idea. Okay? That's what we roughly mean by a limit. So in this case, the idea is when you're approaching 2 on the x-axis, you're approaching 2 on the y-axis like that. The idea is kind of, if you're on the function, the closer you get to 2, the closer that y value gets to 2. Does that make sense to everybody? Okay? And we're kind of building up to something. It kind of takes a while to get students comfortable with this. Next thing I want to do is show you the notation down at the bottom of the page. So we have what we call a two-sided limit, and that would be if it just says x arrow a. That means you're going from 2 directions, from the left and right at the same time. We also have what we call a left-hand limit. That's going to be notated. It's going to say x approaches. That's what that arrow is saying. And then if it has a minus by it, that means it's approaching from the left side. Okay? Then the right-hand limit is represented by x approaches a with a plus sign like that. Now let me just sort of explain what's going on this problem with the left and right-hand limit. Okay, and I got to kind of stand up to show you how this goes. So if you're doing a left-hand limit as x approaches 2, what you're doing is you're only going from the left. As you get closer and closer to that 2, where is that y value going? Isn't that y value just getting closer to 2? So we would say the left-hand limit as x approaches 2 is also 2. The right-hand limit, what you do is you only are on the right side of x equals 2, and you're kind of closing in this way. So as you're closing in, where are those y values going? They're going down, and eventually, don't they get to 2? So the right-hand limit would also be 2. A two-sided limit is just at the same time. Do they come to the same point? Yes. Okay, so the two-sided limit would also be going to 2. So what we say in this problem is we would say, like this, we would say the left-hand limit, and you'd write this like this, you would say the limit as x goes to 2 from the left of 3x minus 4, that would also be 2, and then the limit as x goes to 2 from the right-hand side would also be 2 like that. Okay, we'll look at all kinds of different situations on there. The idea of a limit is the answer is a y value, and it's where that y value is going. Sometimes it doesn't go anywhere. Sometimes it goes to infinity. Sometimes it goes to a point, and we'll kind of see that as we look at different situations. Okay, so is there any question about the notation of the limit, left hand, right hand, or any of that stuff? Okay, I'm going to do one more kind of illustration of this with a calculator, then we'll take a break because we're going to try to work on a lot of this today here. Okay, all right, let's do one more on the calculator. Okay, so on this next example, let's put in x squared minus 4. Now, from your background, do you know what that graph looks like? It's a parabola. What does the minus 4 do? Doesn't flip it upside down. It yeah, it brings it down 4. Okay, yeah. So let's put, what we want to do is put in x. Then there's a x the second button, and then minus 4 like that. And then we'll just use the same window. So I'm going to graph this. So just put that in, type graph, and then we'll get just enough points here. Okay, so I'm going to put, like we have a point 0, negative 4. Okay, and you can trace at any of these values you want to. Like if you traced at 1, or actually you can do this. If you don't know this, students always have different backgrounds. You can also go second graph to get a table to come out. So if you go second graph, you get a table, and then you can plot these points. So for instance, you have, looks like you have negative 3, 5. I'm just going to pick some points from here. Negative 2, 0. Negative 1, negative 3, and so forth. So you want to just kind of fill in some of those points like that. Then that'll give the graph of what that's called a quadratic function like that. Okay? So what we're going to do on this, we're going to fill this table out. And what we're interested in, when we're doing these limits, we're interested in what's happening at -1. Okay? So what I'm going to kind of do on here is I'm going to go to -1 on the x-axis, and just visually I'm going to put like kind of a horizontal or a vertical line through that. Okay? That's just sort of a visual thing here. All right. Now, what we want to do on this is we're going to do the trace again. So I'm just going to do this real quick one more time. So I'm going to trace -2, and let's just fill this chart out together as we do this. So that's 0. Then I'm going to go to -1.1. Okay. And that's going to give -2.79. And then -1. Whoops. It's sometimes so hard to type on here sometimes. -1.01, and that's going to be -2.9799, then -1.001. Let's see, that's going to give -2.99799. Okay, like that. So what's happening to that number, by the way? Where does it look like it's going? -3. Because see, all I'm doing is I'm just making that closer and closer to -1. That's why I'm doing like 0.01, 0.001. I'm just getting closer. I'm doing that on purpose. Now if I go to -1, if I trace at -1, I get -2. Then if I go the other way, if I do like -0.99, that's a number that's a little bit to the right of -1. So that's going to be like... Oh, I got the wrong thing there. That's -3. Okay, sorry about that. So that's -3.00199. Then you'll kind of get the idea of what I'm trying to do here. So -0.99, I do this. I got -3.0199, and so forth. So you're just getting a little bit greater accuracy with the decimals. And then if we go to the last one at 0, that should just be -4 like that. Okay, so the purpose of this, and you're not going to do this on the calculator all the time, the purpose of this is to show you how the decimals work. Yes?
Will the limit always be a whole number?
There are several things. Sometimes it's nothing, and we'll see that in a little bit. Sometimes it's infinity. It doesn't have to be a whole number. It could be a fraction. It could be a square root, like a square root of 2. So there's a lot of different possibilities, okay? All right, so here's what we're going to do then. So the left-hand limit is basically this. The left-hand limit, all you're doing is you're going to the left, and you're closing in on that vertical line. Where's that going? It's going to -3, right? That's the idea. The right-hand limit would be you're going from the right side of the graph. So you're over here, you're closing in until you get to that vertical line, which is -1. Where's that going? It's going to what y value? -3 also. Okay, so that's what that is. Okay, so this is a two-sided limit right here. This one is the left-hand limit. That's going to -3. And then this one with the plus sign is the right-hand limit. So it's also going to -3. Okay, this stuff sometimes a little bit easier for me to just stand up and display. So the left-hand limit is you're going from the left-hand side until you get close to the x -1. So where are you? -3. Right-hand limit, what are you doing? Right side of the graph, you're still at the same value. Two-sided, what are you doing? Same time, and your fingers are coming together, so that's still the same value. That's all I've done so far is that particular example. Okay, does that make any sense? Okay, now the question becomes, why in the world are we doing this? Well, you have to know something about this before you can get to the idea of a derivative, which is kind of the big thing that we'll be leading up to. Okay, we're going to take a 10-minute break. So once you come back at 25 after, and then we'll finish this up. Okay, now this next kind of function we're going to look at, this is something that you are supposed to cover in finite math or college algebra. Is called a piecewise function. And students a lot of times do not graph piecewise functions too well, so pay attention to this. So we're going to graph this without a calculator. So what happens on this, first of all, is you have two pieces. Now, these are lines, so the first thing we're going to do, and this is what you really want to write down, is we have y equals 2x plus 3, and I'm going to have you make a table of values. To me, this is the safest way to learn how to do piecewise functions, okay? There are two pieces. There's two graphs, but they're defined in a certain interval. So when you look at this one right here, that's a line, right? It has a y-intercept of 3 and a slope of 2, but x has to be less than 1. You're not allowed in this table of values to use any numbers other than x's that are less than 1. So what I'm going to have you do is let's start with 1, and there's not an equal to bar, so I'm going to put an open bubble. You want to do that, and I'll explain why you're doing that. Now let's just pick numbers less than 1. Let's do like 0 and -1, and that's good enough. It's a line anyway. So what I'm going to do is I'm going to plug in these numbers into 2x plus 3. So I'm going to do 2 times 1 plus 3. I'm going to work that out. Then I'm going to do, then I'm going to go 2 times 0. So I'm going to do 2 times 0 plus 3, and then I'm going to do 2 times -1 plus 3 right there. Now we're just going to do arithmetic, okay? So 2 times 1 plus 3, that's 5. This is 0 plus 3, so that's 3. This is -2 plus 3, so that's 1. Now we're going to plot those points, okay? And that's what you do in your graph, is you just plot points, okay? So I'm going to do these. Now that 0.15, you want to go to 1,5, but what you want to do is you want to put an open bubble on that, okay? Because that's where it comes to an end. And it doesn't include that because there's not an equal to bar under that inequality. Then I'm going to do 0, 3, put a dot there, -1, 1, and then I'm going to draw a line like that. Okay, now the thing that I see students do wrong on piecewise functions all the time is a lot of times students want to keep going that way. How come it stops there? Because that's what it says, see, okay? It says x has to be less than 1. So as long as x is less than 1, you're on that line. Does that make sense to everybody? Okay, you want to make sure you know how to graph a piecewise function. Okay, now let's do the next piece. Okay, we have 2x minus 3, but this time x is greater than or equal to 1. Okay, and I picked 1 in that previous part because I need to know where it comes to an end. So now what I'm going to do is I'm going to have x, and I'm going to have y equals 2x minus 3. I'm going to go ahead and pick 1, and since there's an equal to bar, that means that will be a solid dot on the graph. That is definitely where it comes to an end. Then I'm going to pick numbers bigger than 1, like 2 and 3, and just all you need is about 2 or 3 points because it's a line anyway. Okay, then we do the same thing. We do 2 times 1 minus 3 this time, and then we do 2 times 2 minus 3, and 2 times 3 minus 3. So we're just doing arithmetic, okay? This is going to give 2 minus 3, or -1. This is 4 minus 3, or 1. This is 6 minus 3, and that's going to be 3 like that then, okay? All right, everybody follow what I'm doing here okay so far? They're doing arithmetic. You got to plug in the right x values. Now let's go ahead and plot these points in this table. So we have 1, -1, but put a solid dot. Then you have 2, 1 over 2 up 1, and then 3, 3 over 3 up 3. So it goes like that. So that is the graph of that function. Now, these two lines don't go on forever in both directions. They stop at 1. When you're below 1, you're graphing 2x plus 3, right? When you're greater than or equal to 1, you're graphing that. Okay, does that make sense? Tell me. Students a lot of times do not do well on piecewise functions. That's the reason I want to make sure that you know how to do this okay. All right. Now, what we're going to do on this, we are going to fill out this table. I'm only going to do this just like one more time. And then this time what I'm going to do, I'm not going to graph this thing. I'm not going to show you how to do that yet. But I'm just going to do this. Okay, so if we're working with 0.9, is 0.9 greater than 1 or less than 1? So where do you plug that 0.9 into? The top one or the bottom one? Top one, right. So we're going to do 2 times 0.9 plus 3. And then the same thing here. We're going to do 2 times 0.99 plus 3. And then 2 times 0.999 plus 3, like that. Okay, now I'm going to go ahead and crunch those things out. I'm just going to do this on this calculator because it's faster. And let's fill those things out. Okay, so I got 2 times 0.9 plus 3. So this value right here is going to be 4.8. And the next one you have is 2 times 0.99 plus 3 is going to be 4.89. Then the next one you have 2 times 0.999 plus 3 is going to be 4.998. Now see, I'm getting close to 1. Where does it look like this number is going?
5.
Okay, it's going to 5, probably, okay. Now here's the thing. Now if x is 1, now you got to be careful about this. If x is 1, where do you plug in? Do you plug into the top function or the bottom one? If it's equal to 1. Now you jump down here, don't you? Okay, so the idea with this one is you have to do this now. Now you have to do 2 times 1 minus 3, which is actually negative 1. Okay, so it goes there. Okay, there's a big jump in the graph right there. Now we're going to do the same thing. Now all of these numbers are bigger than 1, aren't they? Okay, 1.001 is bigger than 1, so where do you plug in, top or bottom? Bottom, because that's what it says, okay? So what you have to do here is you have to do 2 times 1.001 minus 3, and then the rest of them you do the same way. Okay? And then we'll go ahead and crunch those out, and we'll kind of see what's happening on this graph now. So I'm going to go ahead and put these in. So I have 2 times 1.001, and then minus 3, that's going to give negative 0.998. And then the next one is 2 times 1.01 minus 3 is negative 0.98. And then the next one, 2 times 1.1 minus 3 is negative 0.8, like this. Okay? Now we haven't seen this situation yet, but I want to do one more kind of example where we number crunch. So first of all, what we're going to do is I'm going to start with B. What kind of limit is this one? It says x approaches 1 with a negative. What does that tell you? Okay, it's a left-hand limit. So what that really means on this left-hand limit is it means that you want to start from numbers below 1. So we want to go like this. Okay, where is this y value getting close to? It's getting close to 5, isn't it? Okay, so the value of that left-hand limit is going to be 5. The idea is this, okay, you're interested at 1. When you're going from the left, isn't that thing just getting close to a y value of 5? Okay, that's the idea. Okay, now how about part C? Is this a left or right-hand limit? It's a right-hand limit. So what are you doing on the right-hand limit? Well, now you're going this way. You're going from numbers bigger. Look at these numbers right here. Where are they going? Isn't that getting close to negative 1? Yeah, see, when you're real close to 1, just a tad bit bigger, you're very close to negative 1. So that means the right-hand limit is going to be negative 1. So what that means is if you're doing the right-hand limit, you only look to the right side, and then you're getting closer and closer to that y value of negative 1. Does that make sense? Left-hand limit, you're heading to 5. Right-hand limit, you're heading to negative 1. Now the two-sided limit, are these two things going to the same place or different places? Different places. So that means the answer to the two-sided limit is it does not exist. It has to go to the same place. So you'll see that quite a bit, and anytime you see that, you can just abbreviate that with a D-N-E if you want to. Okay, that's what you'll see me do all the time. Okay, so we haven't seen that situation yet, but the left-hand limit exists, the right-hand exists, but the two-sided doesn't, and that's because they go to different places. Okay, does that make sense? Okay?
You would actually list the left-hand limit as 5, it would be 4.5.
No, it's 5. Okay, and see, that's important is it's where it's going. It's kind of like that tortoise and hare thing. Okay, the answer to the limit is the tortoise went 100% of the journey. Even though after 15 steps it was 99.999, it hits 100%. Okay, that's where you're going. That's the purpose of these decimals. And the reason I'm doing this, I'm just making that number real close to 1. If I added another 9 on that, it just gets closer and closer to that 5 anyway. That's the idea, okay? Okay, now let's go to the next page. There was a little mistake on here that you need to correct. What this theorem is saying is it's saying if the left-hand limit and the right-hand limit both have the same answer, then this is supposed to say this is what's wrong. That's supposed to be the two-sided limit. It'll have the same answer also. Okay, that's a basic theorem. Now let me use an example that we already did to explain that. So the idea is just saying if the left-hand and right-hand limit both go to the same place, then the two-sided limit is the same place. Okay, now I'm going to back up to this problem that we did earlier in class right here. Okay, when we did this one right here, we were interested in the limit as x went to 1. Okay, the left-hand limit is going there, isn't it? The right-hand limit's going there. If the left-hand and right-hand limit go to the same place, then what's the two-sided limit? Same answer. Okay, if they go to different places, what's the answer? Doesn't exist. So that's the idea. So if the left and right-hand limit go to the same place, then that's what the two-sided limit is. That's what happened on this example. From the left and to the right, aren't both things going to -3? Mm-hmm. So the two-sided limit is also -3. That's what that theorem says. Does that make any sense to you? Okay. All right, now let's do, we're going to do a couple more things with piecewise functions. Then we're just going to go to graphs, and then we're going to kind of get away from graphs and kind of look at this a little bit more algebraically. So let's go through and do this one. I am going to show you how to do a piecewise on a calculator because a lot of students don't know how to do that. So what we're going to do is, this is a piecewise function with a square root. Okay, so the first table of values, now these are only numbers that are bigger than 0. That says greater than or equal to 0. We're going to go ahead and start with 0, but since there's an equal to bar, that means our graph is going to have a solid dot there. Then you're going to pick numbers bigger than 0. And hopefully you just pick numbers that you know have square roots, like the square root of 1 is 1. What's another number you know the square root of? 4, and then maybe 9. Okay, that's good enough. Okay. So if we do like the square root of 0, you're going to get 0. Square root of 1 is 1, and so forth. You just do that in your head. Okay, and then the square root of 9 is going to be 3. Now what we're going to do is go to our graph, and we're going to go ahead and just plot that out like this. All right, so at 0, 0, we have a solid dot. Then we have 1, 1. We have 4, 2. And 9, I'll just take it out a little bit like that. And then that's what the graph of y equals square root of x looks like, is like that. So you just make a table for each piece, okay? But you want to make sure that you only use the correct x values, okay? All right, now the next one is a absolute value. What kind of numbers do I need to use in my table for x here? Things that are smaller than 0. Now, what you want to do is you do want to go ahead and start with 0 because you've got to figure out that endpoint, but it's going to be open. And then you would do like -1, -2, just whatever you want for numbers that are smaller than 0, right? Well, what are you doing? You're doing the absolute value of each of these numbers. So that's 0. Absolute value of -1 is 1, and so forth like that. Okay, so you're just crunching out that absolute value. All right. So what I'm going to do is let's plot that now. I'll just kind of use a different color. 0, 0, doesn't that just connect with the other graph? Sometimes they connect, sometimes they don't. If they connect, then it's just one big solid dot. Then you have -1, 1, -2, 2, -3, 3, and so forth. Is a V shape. Well, this is half of a V shape is what it is, okay? So that's what you end up having is that graph then. And then what we're going to do is do the limits. I'm not going to do all these decimals anymore. That was mostly trying to see you how things behave close to something. Now we're just going to do this way. All right, so we're going to do a right-hand limit as x approaches 0, okay? So remember, what we're interested in, and you can try this approach if you need to, I'm going to put a little vertical line. It's kind of like a wall through 0. Okay, if I go from the right-hand side, okay, that's what I'm doing with this highlighter. When I get closer and closer to 0, what is the y value getting close to? 0. Okay, so that means the answer to that right-hand limit is 0, correct? Okay, now let's do a left-hand limit. The next one is a left-hand limit. Okay, so what do? I get on the left side and I start closing in. Where is it going? What y value is it going to? 0 again. Good. So that left-hand limit 0. What's the two-sided limit have to be then? 0 also. That's what that theorem said. Okay? So that's the idea. Is it's just, okay, the left-hand limit is going to 0. Right-hand limit is going to 0. Remember, the value of a limit's a y value, and then my fingers come together, so the two-sided limit is the same. That's it. Okay? Now, that's what happens if they connect. If they didn't connect, like the last example, two-sided limit wouldn't exist. Okay, if you don't know how to do piecewise functions on the calculator, I recommend that you learn, because it's a nice thing to learn how to do. And in applications, in economics and business applications, piecewise functions are more common than anything else. It's just kind of the way functions work is you break it up into pieces. So here's how you would put this in. I would recommend that you write this out in this box right here. So what we're going to do is we're going to do like the square root of x. Then you're going to put like a division symbol. Usually what you do is parentheses around the function, division symbol, parentheses, and then put in the condition. I'll show you where those symbols are. Then the next one you have to put ABS of x. Okay, like that. You can have the whole thing in parentheses or leave it off. And then a division symbol, and then x less than 0. Okay, so let me show you how to do this. First of all, what you'll notice on your graphing calculator is you have math and then you have test. See if you can locate that. Test should be there. So if you go second math, it will open up inequality symbols for you. Okay, so you try that and see if that works on your calculator. So there's all your symbols. So you just got to know where everything is. Okay, so what I'm going to do is, you can go ahead and try this with me if you want to. Now I'm going to just do parentheses, square root of x. And some of you will have it like this. Some of you will have to just have x parenthesis x. It depends like that. So that's what you're graphing. Then you do a division. Okay, it's not that you're dividing, that's just separating. Then what you do is you do a new parenthesis, you do x, and then you got to go to your test command. So you go second math. Now what you're going to do is greater than or equal to, like that, greater than or equal to 0, like that. So you just got to know where all the symbols are, and you got to use parentheses in your division symbol or it won't look right. Okay, then you go to the next one. Now the way you have to do this is you have to go, let's see, if you do this, ABS is here. You go to your math button, like that, and then you got to go over to NUM to get ABS. Okay, that's kind of a weird one right there. So it's math, I'll do that one more time, math, then over to NUM, then it's ABS. Okay, so you get that to come out. My ABS symbol comes out, so I do that, I put in an X. Okay, get out of that, and I do a division symbol. Okay, like that. Then what I do is parentheses, then I go X, then I got to go to test, then I got to put in less than 0 right there. It's a little tedious to type all that stuff out, but it's a nice thing to know how to do. Okay, so that's how that goes. You got to get everything put in like that, know where your symbols are. Now if you type graph, it'll do exactly what we did. Okay, and see what it's doing is the absolute value, and then it's doing the square root. So that is a very nice thing to know how to do if you don't know that. All right, okay? And so is there any questions about anything I did with the limits on that piecewise function with anybody? Okay, you want to know how to do piecewise functions by hand, and use your calculator to help you a little bit too. Okay, we're going to do one more piecewise function, and by hand and then with the calculator. Then we're going to kind of get away from that. I'm just going to give some diagrams, and we're going to figure out limits based on the graph. Okay, so let's go ahead and start with x plus 2 with x being greater than 2. Now, when you do your graph on this, what kind of numbers do you want to use for this in your table? 2 and bigger. Now, you do want to start with 2, but you want to have an open bubble because there's not an equal to bar there. If there's an equal to bar, that's going to be a solid dot. Okay, then just pick numbers bigger than 2, like 3 and 4, and however many you want. That's good enough. Okay, and we're just going to plug in and do x plus 2. X is these numbers, so we're going to do 2 plus 2 is 4. We're going to do, 3 plus 2 is 5. and 4 plus 2 is going to be 6. So those are good enough dots. Let's go ahead and go to our graph and plot those out. So we have over 2 up 4 with a open bubble. We have 3, 5, and then 4, 6, and that line just goes in one direction. Starts with 2 and then goes to the right like that. Okay, and then the second graph is going to be a quadratic. What kind of numbers do I need to put in my table on this one? 2 and smaller, right? Okay, so I'm going to start with 2 with a a solid dot this time because of the equal to bar, and then just start picking some numbers smaller than 2, like 1, 0, -1, -2, and so forth like that. Just do the arithmetic. So you're doing x squared minus 2. So that's 2 squared minus 2, which is 2. 1 squared minus 2 is -1. 0 squared minus 2 is -2. -1 squared minus 2 is 1 minus 2, so that's back to -1. And then -2 squared minus 2 is 4 minus 2, so that's 2 like that. Okay, be careful with your squaring. You square a negative number, you get a positive, right? So now we're just going to plot these points. So we have 2, 2 with a solid dot, 1, -1, 0, -1, or -2, and so forth like that. Okay, and then that's how that piecewise function goes. So if you're doing this by hand, that's what I recommend you do, is just do 2 tables of values, because it's all arithmetic anyway, and then plotting points. Does everybody understand why this has an open bubble and that has a solid? Okay, all right, that's because that had an equal to, right? Okay, that's the thing, all right? Why can they not both be solid? That's a good question. It wouldn't be a function, okay? Because if they both had a solid dot, it'd fail the vertical line test. So you always kind of have that situation. Okay, now let's figure out the limits on this then. So the first one is a right-hand limit, okay? What we're interested in, and I think I have a mistake on this too. I did not mean for this to be 0. I meant for that to be 2. So please change those zeros to 2. I mean, you could do it at 0, but that's not the part of the graph I'm interested in. I'm interested in the part where there's a break. Okay, let's do the right-hand limit, and I'll do that kind of in yellow. So again, what I'm doing is when x is equal to 2, that's kind of the number I'm interested in. Okay, right-hand limit. Can you tell me where that's going? What y value? Where's it going? Remember, it's a y value. 4. The answer is 4. The answer to a limit is a y value, right? Okay, you're getting close to that y value of 4, correct? Okay, the next one is a left-hand limit. Okay, I'll use my highlighter on that. Can you tell me where it's going? It's going to 2. Okay, good. Everybody got that? Remember, the answer to a limit is a y value. Okay, how about the two-sided limit? Doesn't exist. Good. Okay, it's got to go to the same place. Okay, so again, a two-sided limit, just always do it this way. If your fingers don't come together, then it doesn't exist. Okay, left-hand limit goes there. Right-hand limit goes to 4. Two-sided doesn't exist. That's the idea. Okay. All right. Now I'm not going to put this in the calculator. If you want to just write down as a note to yourself how you put this in, you can do this. So you just kind of go like that. Then the next one you'd say x squared minus 2. But always put that division symbol in there because sometimes it won't work out right. It's just you got to use that as a separator. Okay. All right. Any questions? Okay, now what we're going to do is I'm going to go to this next page, and what we're going to do is just I give you a graph, you tell what the limit is. So that's kind of a big thing that we're trying to kind of get established here. Okay, so first of all, on this graph, on this example, the first thing I want to do is I want you to know what function values are. Like A, B, C, and D, you're not doing calculus, you're just telling me what the function value is. And that's important. So what the meaning of f of -8 is, what this means is just means x is -8. What is y? That's what you're asking for. If I'm asking for a function value, I'm giving you an x value and you're telling me what y is, okay? So here's where x is -8. Now what happens on this graph? You have a bubble there, then solid. The function is here, right? What is the y value of that point? -3, right, okay? So that would end up being -3. All that means is you just have a point, -8, -3. That's what you have. Okay, go to -2. When you're at -2, what is the value of y? There's a solid dot there. What is its y value? 3. Okay, so that is 3. Okay, again, that just means that you have the point, -2, 3, like that. That's a function value. Okay, go to 6. When you're at 6, you have a bubble and then a solid. Where is the function?
5.
Yeah, it's there. Okay, it's wherever the solid dot is, so that's 5. Okay, so that's going to be 5. And again, that just means you have the 0.65. Okay, how about f of 10? 0, right. Okay, so that's just the 0.10, 0 like that. Those are function values. Those are not limits. Okay, now we'll kind of go through and begin to look at these limits. So we're going to start with 8. Okay, and hold on, I think I missed a minute. Let's see, I have 6, 10. I think I didn't type this one right either. I think what no, that's right, -8. -8's good. I want to look at -8. Okay, all right. So let's start this way. Now this one is a left-hand limit here. This is a right-hand limit, and then the last one's a two-sided. Okay, so what I'm going to do is I'm just going to think, okay, kind of take a vertical line going through like that. Now watch this carefully because sometimes students do not understand this well. Okay, left-hand limit. Where am I going? -6. Okay, it doesn't matter that the function jumps up. That doesn't matter. It's where you're going. You're going towards -6. Okay, so that value of that left-hand limit is -6. Okay, right-hand limit. I'm going to get to the right of that vertical line. Where's it going? It's still going to -6, isn't it? Okay. All right. How about the two-sided limit? Same place. Okay. Don't worry about the fact that that function jumps. That doesn't make any difference. The limit is where it's getting close to. It's getting close to -6. It doesn't ever hit -6. It just gets infinitely close to it. That's the idea. All right. Let's go to 6. So now we're going to look at the limit as x goes to 6. So I'll put a vertical line through at 6 like that. Okay. Left-hand limit. Where's the left-hand limit go? 2. Okay. It's going towards the y value of 2. So you have a left-hand limit going to 2. Okay. How about the right-hand limit? Is it going to the same place or someplace different? It's going to 5. Good. Okay, so that's going to 5. Okay, what's the deal with the two-sided limit then? Doesn't exist because it goes to a different place. Everybody got that? Okay, remember the answer is a y value. It's whatever that y value is getting close to. Okay, now let's look at the next one, number at 10. Okay, so 10 is okay. So I'm going to put a vertical line through 10 and take a look at that. So if I'm going from the left of 10, what is the y value getting close to? 0. Okay. If I'm going from the right of 10, where's the y value going?
0.
Same place, 0 again. What's the two-sided limit then? 0. Okay. Now see, here's how that theorem goes. If the left and right-hand limit are the same, then that gives you the answer to the two-sided limit. If they're different, what do you get on the two-sided limit? Doesn't exist. That's how it goes. You just kind of trace it out. That's one of the things that you want to be able to do. Okay, is there any questions about that? Okay, let me ask one more thing on this. What if we were doing the left-hand limit as x goes to -2? Where would that be going? 3. How about the right-hand limit? Infinity. Okay, which we'll see that a little bit in the next class. Okay, so it can go all kinds of different places. Okay, this next question says, is it possible to define f of -8 so that the limit as x approaches 8 is the same as the function value? And pay attention carefully to this. Okay, here's -8. What was the value of this limit Two-sided limit, what was the value? What's the function value? They're different, right? So all I'm asking is, if you wanted to define this so that the value of the limit was the same as the function value, what you would do is you would want to make that function value also -6. That's what that statement right there is saying, is redefine this so that it's equal, so that the value of the limit becomes the value of the function. So what you would say is this, you would say, yes, you just say let f of -8 be equal to -6. Okay, in other words, all I'm saying is just move that dot down there, fill in the bubble. Okay, that's what I'm saying. Then the value of the limit is the same as the value of the function. Right now, the limit has a value of -6, but the function is -3. They're different. The limit still exists. Okay, that's one of the situations sometimes students are a little unclear about. Okay, so let me have you guys work on the next problem. Just going to give you a few minutes to see if you can fill this out and see if you kind of absorbed what I'm trying to teach you today. There's a purpose for this, but it always takes several classes to get the limit down, because you have to understand that to understand how derivatives work, and derivatives are a pretty big deal. Or some of this. So let's look at making sure you've got the function values right. So if x is -1, then what's y? Okay, so that's 1, right? Now, not a limit, that's a function value. How about this one? If x is 0, which is there, what's the value of the function? It doesn't even exist, okay? It's undefined, okay? I mean, there's not a solid dot there, is there? Okay, we haven't seen that so far, but if you just have an open bubble and nothing else, the function is undefined. Now, you can say does not exist too if you want to. Okay, if x is 1, what's the value of the function here? 2, yes, okay, it's that point right there, so that has a y value of 2, okay? All right, if you're at 3, what's the y value of that point? Okay, so has everybody got that okay? Okay, those are function values, okay? Now we're going to look at limits, so we're going to look at, this one is a right-hand limit here, and then a left-hand limit, and then the two-sided limit here. So we're going to look at around 0, okay? So I'm just going to kind of have that dashed line through that. Okay, what is the right-hand limit? 2. Okay, good. All right. Left-hand limit around as x goes to 0, what's that? 2 also. So therefore, what's the two-sided limit?
2.
Okay, so that's easy. Once you know that they're the same, so is the two-sided limit. Okay? All right, now let's go to -1. -1, I'll put like this dashed line through like that then. Okay, now this one was a left-hand limit, then a right-hand limit. You got to pay attention to the notation. Okay, so what's the left-hand limit?
Regular 1.
What's that?
I think you're just looking for regular 1.
Oh, we're looking at 1, aren't we? Okay, sorry. Okay, let's try that again. All right. Seeing too many negatives there. Okay, what's the left-hand limit around 1? Yeah, it has a y value of -1. Okay, good. What is the right-hand limit? 0. Yeah, no, look at that function value. Only look where it's going. What do you conclude about the two-sided limit? Does not exist. Okay, good. Okay, now we want to go to 3. Okay, what's the left-hand limit? 0. So that one's 0. That's your left-hand limit on that one. Okay, what's your right-hand limit? Has a y value of 1. Okay, what do you conclude about the two? I think that one right there said, I think I was intending for that to be, I kind of did a bad job of typing this. So change that to x approaches 3. So what do you conclude? Does not exist. Okay, that's how that gets. Okay, all right, how'd you guys feeling about this? Okay, it's just all a matter of interpreting and understanding function values and graphs and how that relates to a limit. It's the idea. Now, this question here says, can you define the function at f of 1 so that the value of the limit is the same as the function value? So let me erase some of this stuff that I put on here. Now, let's just see what's going on when x is 1. Okay, so when x is 1, we're really interested in this. Okay? So, is there any way to move that dot? So it would the only way to get the two-sided limit to come to a number is if they both connect, right? Is there any way to connect that? No, there isn't. There's no way to do that. So the answer to this is no. Okay, you just can't do that. You could move that dot down there, but it still wouldn't connect the graph. So there isn't anything you can do on that one. Okay, now let's look at 3. Okay, now how about that? Is there any way that you can connect those two? No, there isn't. Okay, so that's also no. You can't do it. Okay, so that's kind of the idea. Now, if you wanted to do, like make the value of the limit equal the function value here, you could say f of 0 is 2, and then you would fill in that dot there. So that's basically what that's saying. Okay. Okay, well, let's finish up here with what we're going to kind of get away from now is away from graphing and just look at this algebraically. So let's just see if we can get through a couple other key things here. Okay, so we're going to look at the limit of a linear function. Okay, so a linear function, you want to know, has the form f of x equals mx plus b. We've already graphed some linear functions today. Okay, what's m? M is the slope. What's b? That's the y-intercept. So that's background knowledge that you want to make sure that you know. And of course, the graph of a linear function is just a straight line. Okay, it's always going to be some straight line with some sort of a slope. So what happens when you're doing a limit of a linear function, you don't have to graph. All you got to do is just plug the number in. Okay, and the idea is there's no breaks in the graph or anything like that. The value of the limit is going to be the same as the value of the function. So what this theorem is saying is what it's saying is if you're doing the limit of a linear function, just take that number and plug it in for x. You just do arithmetic, and you're going to start doing, when you start dealing with getting away from graphing, most of the time you're just going to plug the number in and see what you get. Okay, so all of these things on example 14 are linear functions, right? 3x minus 7 is a line. 5x is a line. Is 4 a line? How do you graph y equals 4? Not that way, this way. Okay, it's because what it really is it's y equals 0x plus 4. Y-intercept of 4, 0 slope is this way. So they're all lines. So what you would do on this example A is you would just do 3 times 4 minus 7. So you just take that 4 and plug it in. You'd have 12 minus 7. So the value of that limit would be 5. If you graphed it out, that's clearly what the limit would be going to. The left and right hand are always going to go to the same place on a line. They have to, okay? Next one, you just do the same thing. Okay, you just say 5 times negative 9, so you get negative 45. Okay, that's it. Okay, no graphing required. Okay, now this next one thing that you might want to do that might be helpful is draw a little graph of y equals 4. That's the graph of y equals 4. Now what you're interested in is the limit as x approaches 6. Well, if you did the left-hand limit, where would that be approaching? What y value? Isn't the y value always 4? Okay, how about the right-hand limit? Isn't that still 4? So what's the answer to the limit? It's got to be 4. Okay, so if you have a limit just of a constant, it's going to be the same. Okay, how about y equals pi? Is that a line?
Yes.
Sure it is. Pi is about 3.14, so actually this graph would be it would be like somewhere between 3 and 4, like that. That's what the graph of y equals pi looks like. So the answer to that's just going to be pi. Okay, that's it. Okay, so anytime that you have a limit of a linear function, you don't have to graph it, you just plug it in. Okay, and we'll kind of finish that up a little bit next time. So we just got a few more things to do. It probably takes about 15 minutes on Thursday to wrap this up, and then I'll give you the next handouts on Thursday. Okay?
So syllabus quiz due Thursday.
Syllabus quiz, yeah. Just have that by midnight Thursday night. Try to have it done as fast as you can. And you can go ahead and get in my math lab and start homework. So it's always good to do it while it's fresh in your mind. Okay? And I'll post the recording of this. So you can always look at that if there's anything you need to review. You don't have to watch the whole thing. You can fast forward and find if you need to review something, you can.